curve. You have a particular point on the curve that you're doing all your calculations at. And the osculating plane will be the plane that's the best fit to the curve in the immediate neighborhood of your point. So if you just take a little piece of curve and you try to imagine it lying on a plane, what is that plane? It's actually lying on the plane. So in the context of our picture, that the osculating plane is the page that you've drawn the curve on. Of course, most space curves are not planar. Most curves, space curves, do not exist on one plane throughout. But what you're doing is you're just looking at one little bit, okay? And you're saying, what plane does this one little bit seem to lie on? That's the osculating plane. The normal plane chops right through your curve like you bring a big axe and you're chopping right through it, and it's along that dotted blue line. So that would be your normal plane. The tangent plane to the curve. Now we will be talking a fair amount about tangent planes in this course, but we'll mostly be talking about tangent planes to surfaces, not tangent planes to curves. But were we to talk about the tangent plane to the curve, it would be lying also it would also stick out of the page, but it would be orthogonal to that blue dotted line. It would actually lie along that R-T line. Okay, that would be. So you'd have your osculating plane holding the curve, as it were, your normal plane chopping right through it, and then your tangent plane orthogonal to both of those planes. Okay, so I did a little bit of text on osculating plane and on the normal plane. Tangent plane, which is the least important of these three. And I'm just going to write here to the curve, even though that might seem obvious, because later on we're going to be doing lots of tangent planes to surfaces, so I just want to highlight that this is different. Tangent plane to the curve is orthogonal to the above planes and is determined by T and B. Yeah. B is sticking straight out of the page at us. T was lying along that red line, and B and T between them would define the plane, would determine the plane. Okay, so the normal to the osculating plane, and I've already written this towards the top. I shouldn't say the, in fact, I'm going to rub that out. In fact, I'll cross it out just to make it really obvious. I should say a normal to the osculating plane is r dash crossed with r double dash. Of course, there are infinitely many normals to any plane, because a normal is simply a vector that's pointing out. You can think of it almost as an arrow that's pointing orthogonally out of your plane, and there are infinitely many of those. They'll all be parallel to one another, but they could be different lengths, and some could point up and some could point down, and so that gives us ultimately infinitely many. All right, and just to go back up to the picture, R dash and R double dash are lying on the page. If you cross them, you end up with a vector that's sticking out of the page, and hence that vector is usable as a normal to the plane that is the page. Okay, but what about that dotted blue line? If we want to find a normal to that dotted blue line, well, it's there in the picture. A normal to the normal plane. Sorry about that. The word normal is being used in two senses there, because this word normal here, this is the plane that is normal to the curve. Okay, so hence it's called the normal plane. This is the normal that's normal to the normal plane. Just roll with it. Is just R dash. And if you go look at that picture, the red arrow R dash is orthogonal to the plane that's indicated by the blue dotted line. So a normal to the normal plane is just R dash. Okay, so let's do an example. Okay, I'm going to do a page jump. Everybody prepared? I'm going to do example 52. Example 52 says find the normal plane and osculating plane for R of t equals, oh look, it's a twisted cubic. Okay, this is easy stuff. Said already, some stuff in this course is tricky, some stuff is easy. This is easy stuff. Make sure that the easy stuff you can do. Okay, I'm going to work out r dash. 1, 2t, 3t squared. I'm going to work out r double dash. 0 to 6t. Okay, please keep quiet. I want to know what r dash and r double dash are at my point. My point is the point 1, 1, 1, but r dash and r double dash are functions of t. So in order to find out what r dash and r double dash are at my point, I need to know the value of t at my point. It's pretty obviously 1. How did I get that? T equals 1 is the number that I need to substitute into r in order to get out the point 1, 1, 1. So you have to do it by inspection. What does by inspection mean? It means by looking at it and figuring it out. Fancy way of saying you look at it and you scratch your head for a little while and you go, the answer is. And that's called solving something by inspection. So what's r dash of 1? 1, 2, 3. What's r double dash of 1? 0 to 6. Okay, oops, I left out my dash. There we go. So I'm going to cross r dash and r double dash, and I'm going to call it n. Oops. Okay, 1, 2, 3, 1, 2, 0, 2, 6, 0. To do your cross product whichever way makes you happy, as long as you get the right answer. This is how I do it. Let's have a look. It's 12 subtract 6. It's 0 subtract 6. It's 2 subtract 0. There we go. There's my normal. That's the normal to the osculating plane. So my osculating plane is 6x minus 6y plus 2z equals what? Well, I'm going to have to plug in my point. There are infinitely many planes that start 6x minus 6y plus 2z. The way to get the unique plane that we want is we want the one that the point 1, 1, 1 satisfies. 6 minus 6 plus 2, that's 2. There we go. How did I get that 2? 6 times 1 minus 6 times 1 plus 2 times 1. That's my osculating plane. And that's great and that's lovely. If you want, you can divide by 2 throughout. But you don't have to. Okay, so that's my osculating plane. A point of interest. I understand that the word osculate in mathematics is generally used for things that touch. So osculating curves are curves that touch and then move away from one another again. And I have been informed that it comes from a Latin word meaning to kiss. The curves kiss, or the plane kisses the curve. I have other friends who can actually speak Latin who say they haven't come across this word, so I don't know whether it's obscure or whether my information is incorrect. But I have seen it in quite formal sources, so there you go. So impress your friends. Use the word osculate in casual conversation before nightfall. Just make sure they don't speak Latin in case you do it wrong. Normal plane. Okay, the normal plane is easier, no calculation required. The normal to the normal plane is just r dash, and that's, what is it, 1, 2, 3. So 1x plus 2y plus 3z equals what? Equals whatever it needs to be equal to so that the point 1, 1, 1 satisfies it. 1 plus 2 plus 3, 6. Once again, how did I get that 6? 1 times 1 plus 2 times 1 plus 3 times 1. Easy, right? You try number 53. All right. Limits and continuity. And ultimately differentiability, but it'll be a couple of days before we get to that. So T and N both lie on the page, if you will. They lie in the same plane as the curve, or if that curve were not planar, they lie in the same plane as that little piece of curve near the point. So T and N are lying on the osculating plane. And so the sort of formal definition of osculating plane is the osculating plane is the plane that's determined by T and N. It's the plane that T and N are lying in, and if you have two vectors that are non-collinear or non-parallel, then between them they always define a plane. If you take any, if you take your pen and you take your pencil and you put them next to one another and you make sure they're not parallel, your pen and your pencil between them will define one unique plane. And so T and N are between them defining a unique plane, and we define that plane as the osculating plane. When we come to actually finding its formula, the formula of the osculating plane, we're not really fussed about which normal we use, because we just want a normal that works. So we could find T and we could find N and we could cross them to find a normal to the osculating plane, and that would be totally fine. But it's overkill. We don't need to do that, because R dash and R double dash will do the job just as well. And they're much easier to find than T and N. So T and N, the formal definition of the osculating plane is that T and N determine the osculating plane, where T and N are very well-defined vectors to do with unit normal vectors and unit tangent vectors. But to actually get the formula of the plane, we're really not fussed, and so we just cross R dash and R double dash because they do the job. Okay, all right. Same with T and B. So B is pointing out of the page there where the red dot is. So T and B together define the tangent, determine a tangent plane, and B and N between them determine the normal plane. Okay, all right. I really need to carry on with limits and continuity, so here we are. Okay, new section of the work. I'm going to get my notes just right. Okay, so first I'm going to do a little bit of a revisit of limits. We're going to be looking at limits quite a lot, and continuity kind of comes along for the ride, but it's really limits that are the main thing. So in R2, back in first year calculus, we write that the limit as x tends to a of f of x equals L. That would correspond to a picture that would look something like this. Here's a curve, here's a, here's little l, here's y, here's x, and here's my function. Okay? Now that picture and that limit statement there go together. As x approaches a, y approaches L, all right? And we can approach x equals a from two sides. We can approach it from the right or from the left. We tend to say we can approach it from above and from below. Okay, so you can have two one-sided limits. X can approach a from two directions. If the limit as x approaches a from below is equal to the limit as x approaches a from above, then we say the limit exists. Otherwise, it does not exist. Okay. Continuity is a stronger thing. Let me just mention continuity, even though limits themselves are our focus here. For the function to be continuous at x equals a, the limit must exist. The function must be defined at x equals a, and the limit must equal the function value. So there's three things going on. That definition of continuity is still applies for two variable functions, but the limits are harder to work out. So I just want to number these things. Number 1, the limit must exist. Number 2, the function must be defined. And number 3, the limit must equal the function value. There's 3 things going on there. Okay, but to return to limits, let me put little arrows in here. Now that x-axis, that is the domain of our function. Or if our function has a very defined beginning and end, perhaps only a piece of the x-axis is our domain. But my point is, those little arrows that I'm drawing there, I'm drawing them on the domain. My x-axis, or an interval on my x-axis, is my domain. A is a point in my domain. If I want to pass through my domain towards that point x equals a, I have to move along those arrows. Okay, I'm really belaboring that because I want to now jump that upper dimension to 2 variable functions. Okay, in R3, okay, so that curve was a curve in R2. In R3, we write, the little algebraic statement is very similar. Instead of saying x is approaching a, we say xy is approaching ab. Our function, instead of being f of x, is f of xy. And it's equal to, well, still some function value. I'm going to call it capital L here. And what would be the picture? The picture would be something like this. Okay, let me try and draw something 3D. Let's say we've got some piece of curvy surface here floating in space. Here I've got my point AB in my domain. My domain is now the xy plane, or maybe a region in the xy plane. So that's my point in the domain. It's no longer a dot on an axis, it's a dot on the xy plane. And the function value that my function is tending towards is some spot on that surface. Where L would be some value on the z-axis. Okay, sure, fine. So the little algebraic statement just picked up a variable, not a problem. We went from 1 variable to 2 variables. Our picture is now a picture of a surface, not a picture of a curve. Okay, fine, but still, everything seems fine. But here is where it gets not so fine. Those little arrows. If we want to approach the point AB, we can't just approach it from 2 directions. We can approach that point AB from infinitely many directions. So we've gone up 1 step, we've gone up 1 dimension in our function, but instead of going up 1 dimension by 1 little arrow, it's not like we had 2 little arrows and now in this picture we're going to have 3 little arrows. We actually have infinitely many little arrows, which is awkward, to say the least. Okay, I'm going to draw lots of little arrows here, all pointing at AB. XY can approach AB from infinitely many directions and if any 2 of those well, I don't want to call them one-sided limits, if any of those direction-dependent limits disagrees with any of the others, we will say our limit doesn't exist. Any 2. So, infinitely many directions, and if any 2 directional limits differ, then the limit does not exist. Which isn't so great. It kind of adds to your workload, because if you want to find out whether the limit exists, it becomes quite a big deal to figure out whether the limit exists. There are some functions where we completely take it for granted that the limits all exist. All our beautiful quadric surfaces that we have in that double page early in the handbook, all of those are continuous everywhere. Their limits exist everywhere. Those are the sort of common or garden surfaces that people recognize and understand, and we know that everything is lovely and continuous and differentiable. Well, except for cones. Cones have a spot where they're not differentiable, but they're still continuous everywhere. But you end up with really weird functions. If you want to look in your handbook on pages 26, 27, 28 a bit, and then later on when we hit differentiability, pages 31, 32, you look at those functions. Those are bizarre looking functions. Most of them are piecewise defined. And just to say off the top of your head whether those things are, have limits that exist, or whether they're continuous, or whether they're differentiable, you can't. You've got to do a whole bunch of work before you can answer those questions. Okay, all right, so what do I want to say next? All quadric surfaces. Okay, so those are all those pretty little surfaces in that double page there. Are continuous and differentiable everywhere, except cones have one non-differentiable point. But except for that one little caveat, they're continuous and differentiable everywhere. All limits exist everywhere. More complicated surfaces require some investigation. You have to be a mathematical detective. Okie dokie, so it's probably best demonstrated with an example. In fact, I'm going to do 3 examples, each slowly increasing in complexity. Question at the back.
Do our hemispheres fit into the differentiable everywhere?
Well, I suppose any surface that has an edge is not differentiable on its edge. Yeah, so I suppose hemispheres would not count there. But other than on its edge, we would say it's differentiable. So yes, true enough. I wasn't thinking of surfaces with edges. Even a paraboloid, if you stop it somewhere so it's got an edge, it won't be differentiable on its edge. Caveats. Okay, but I'm going to demonstrate. So for the next little while, certainly today and possibly tomorrow, or certainly the first half of tomorrow, I don't know, certainly today, we're going to be looking at cases where the limits don't exist. Okay, we'll move on to where the limits do exist, which, believe it or not, are harder to prove. It's easier to prove limits that don't exist than that do exist. So I'm going to demonstrate with 3 examples. The first one is number 60. Does the limit as xy tends to 0, 0 x squared minus y squared over x squared plus y squared exist? Okay, we want to know, does it exist? And if it exists, then what is the limit? Okay, I'm going to draw a domain picture. Here's my domain. Okay? Except my function is not defined, my function itself is not defined at 0. So for instance, if somebody said, is this function continuous at the origin? Please keep quiet. We could immediately answer no, because it would break number 2 of those 3 things. Remember, those 3 things are numbered to do with continuity. And the second one is the function has to be defined there. So this, and the function's not defined at the origin. So our function is definitely not continuous, but even so, the limit might exist. If you picture a surface that has a little hole in it. You come along with a pin and you've pricked a little hole in it. Your function is not continuous where the hole is, but the limit still exists, because it doesn't matter how you approach that hole, you're still approaching one consistent z value. So the limit would still exist, even though the function itself would not be defined. So that's what we're trying to find out. We know that there's a hole, but is it just simply a hole, or is it some dreadful singularity where the function, the limit itself is not defined? Okay, all right. So I'm drawing a dot there. Now the origin itself is not included in my domain, but I'm trying to make it obvious the point that I'm interested in. And what I'm going to do is I'm going to approach that point along the x-axis and also along the y-axis. Okay, if you want to actually draw a little open circle for that red dot, maybe actually that would be wiser. Let me try and do that. Let me do that. I'm not trying to say that the dot's included. I was just drawing the dot to show this is the point I'm interested in. But just to be technically correct, let me draw a little open circle. All right, so what we're going to do, I'm going to approach 0, 0 along the x-axis. Now the x-axis is the line where y equals 0. So I'm going to say the limit as x0 approaches 0, 0 of x squared minus 0 squared over x squared plus 0 squared. Okay. Everywhere along those horizontal black arrows over there, those are along the line y equals 0. Every point along those black arrows has a y component of 0. Y is not changing, only x is changing. Okay? So this is the limit of x0 approaches 0, 0 of x squared over x squared, which is 1. The limit of 1 is just 1. X can tend to whatever it feels like tending to. The limit of 1 is 1. X can tend to 1, it can tend to pi, it can tend to infinity, it can tend to whatever it wants to. The limit of 1 is 1. Okay, let's do those vertical black arrows. Approach 0, 0 along x equals 0. Now we have the limit 0y tends to 0, 0 of x, no, sorry, not x. We're replacing x with 0. 0 squared minus y squared over 0 squared plus y squared. So you can see what's going to happen here. We have minus y squared over plus y squared, that's minus 1. And the limit of minus 1 is minus 1. So, our function x squared minus y squared over x squared plus y squared, that is a surface. That is a surface, we could draw it. Not sure what it looks like, but if we spent a bit of time at it, we could draw it. And it's a surface. And so what you can do is you can think of, if you've been in my class before, you know I have some tendency to say this, you can think of a little ant. Little ant walking along the surface, vertically above or maybe below, depending where the surface is, but vertically in line with the x-axis. And the little ant is walking along the surface in line with the x-axis, like over here. Here's my surface, whatever it looks like. And I've got an ant walking along the surface like this. Okay? And as far as that ant is concerned, it appears to be walking towards the z value, z equals 1. And it's got a friend on the other side, and they're doing this, and they're walking towards z equals 1. But whatever our surface is doing, and I don't know what the surface is doing, there are two other little ants walking along here above the y-axis. And they're equally positive that they're heading towards z equals minus 1. So there's a disagreement. There's a disagreement. The limit from along the one line, along the one path, is z equals 1. And the limit along the other path is z equals minus 1. What's happening at the origin? Well, crazy stuff's happening at the origin, and the limit doesn't exist. Okay, crazy stuff is not a technical term, but the limit does not exist is a technical description. The results disagree. The limit does not exist. So if you have a function where the limit does not exist, it's then your job to find two paths that disagree. And if you have a limit and it looks like the limit equals 1, and you find a different path and it says the limit equals 1, and another path and the limit equals 1, and another path and the limit equals 1, who knows? The next one that you choose might give you something else. So you have like 100 paths, and the 100 paths each lead to a limit of equal to 1. Does your limit exist? You don't know, because maybe your 101th path would be your lucky one, where you'd find a different answer. So what I'm doing here is I'm setting up for limits that do exist. Limits that do exist would need a different process. Question? You, yeah.
What do the 1 and minus 1 actually represent?
They represent z values. Now, of course, there is no actual z value at the origin because your function's not defined. But it's the z value that looks like it should be the z value if your function actually were defined. But there's a disagreement because depending on what direction you come, and so then you just kind of say something crazy is happening with this function, limit does not exist. Question over there?
So you can actually choose any two paths.
Yes, correct. You can choose any 2, 3, 4, 5 paths you want. Of course, you only need 2 that disagree. But it takes a bit of practice to look at it and go, haha, I know your secret function. I know that if I just choose this path here and that path there, I'll prove the limit doesn't exist. But after you've done a bunch, you start to get a bit of a sense. Oh, it's that sort. It's that sort. Or you can look and you can go, in your head, you can go, I can see if I choose the first 3 paths I'm thinking of, I'm going to get the same answer. Let me be creative and think of a different one. Okay, but that's what I'm about to demonstrate now with 2 more examples. Yes. Could you please be quiet? I can hear the question.
How
Okay. Oh no, I didn't. Okay, so there's a my function itself is not defined at 0, 0. I cannot substitute x equals 0, y equals 0 simultaneously into my function. In that first approach, I set y equal to 0, but I did not set x equal to 0. I allowed x to approach 0. It's different. It's different. In the second approach, I set x equal to 0. I did not set y equal to 0. I allowed y to approach 0. In the end, it didn't actually matter whether x and y were approaching 0 or approaching something else, because it was just limit of 1 and limit of minus 1. But let's say that this one here, let's say it actually been limit x, not limit of 1. Then I would have said equals 0, because the limit of x as x approaches 0 is 0. And you're not saying x equals 0, you're saying x is approaching 0. Limits have a very strange existence in mathematics teaching, not pure mathematics, but in mathematics teaching, because limits are so fundamental to calculus, so absolutely fundamental to calculus. And you can all do calculus, and I know you can do calculus, and by the time you leave this course, you're going to be able to do multivariable calculus. And at the same time, a lot of you are going to leave this course not truly understanding limits, and it's this weird, I don't know, it's this weird conflicting identity that limits have. They are so important in calculus, and yet they are such a hard concept to really feel in your gut. But they are so important. So if you're looking at limits and you're thinking, I don't really get limits, well, you're with a lot of people, because a lot of people don't really get limits. And the fact that you're really thinking about it and really tussling with it in your mind is very valuable, because limits are so important in calculus. There's nothing more important in calculus than limits. And limits are about how things behave as something approaches something else, not how it behaves as something actually equals something, but as it approaches. It's all about approaching infinity, approaching 0. Anyway, I don't know whether that answered your question, but I just thought I'd wax philosophical about limits for a second. 61. Again, 0, 0. What's the time? Got to watch the time. X, y, x squared plus y squared. We've been asked, does this limit exist? Okay. I'm going to draw a domain picture again. We want to approach that point. And I'm going to approach, let's have a look, squared 2x equals y. I'm going to approach along one of the axes. I don't really care which one. Let's go for the y-axis. That's going to be my one path of approach. My other path of approach is going to be along the line y equals x. In fact, I'll tell you what, let's include the x-axis as well, but you'll see that the x-axis and the y-axis actually agree in this particular problem. Okay, I'm running out of time. I only have 4 minutes, so let me do this speedily. Approach. Yeah. Well, that's the painful thing. So for the sake of the audio, I'm asked, how do I know that y equals x is going to be a useful path to approach on? That's what you're asking. Experience. Oh, man. And I wish I could just like plug an experience mod into your head. No, but that's what you're going to get by doing a bunch of examples. I will show you what happens, and you will see that after you've done a few of those, you start to recognize what's going to happen ahead of time. Let me do it. Okay, along x equals 0, that's the y-axis. It's going to be the limit 0, y approaches 0, 0. So x is equal to 0, y is approaching 0. So it's going to be 0 over y squared. Okay? I'm sorry, I'm at the end of my page, so it's just going to do a jump, but I'll scroll up. Okay? Because if I set x equal to 0, I'm setting my numerator to 0. What if I approach along my x-axis? You'll see you'll get the same story. Approach 0, 0 along y equals 0. Once again, I'm going to have a numerator of 0. So my x-axis and my y-axis, the ant walking along over here and the ant walking along over here, they agree. They're saying, I'm heading towards z equals 0. So am I. Yay, agreement. But the ant that's walking along above the path y equals x, that one's going to disagree. Approach 0, 0 along y equals x. Okay, so limit. I'm just going to make both my variables the same letter, okay, because y equals x. So I'm going to make it x is approaching 0, 0. I'm replacing all my y's with x's, so I'm going to get an x squared at the top and x squared plus x squared at the bottom. X squared over 2x squared is just a half, and the limit of a half is a half, whether x is tending to 0 or pi or 10 or 1001. X can tend to whatever it feels like. The limit of a half is a half. And that disagrees with the 0. So the ant that's walking along over here, where's my y equals x line? The ant that's walking along over here is saying, no guys, girls in fact, I think the ants that are actually out and about in the world are girl ants. No girls, we're actually heading towards z equals a half. I totally disagree with you, 0. Okay, don't call me on my entomology here. I don't know anything about ants. Yes?
Is there a reason why you use x specifically?
Could have used y.
And if you've used like a different variable as well?
Oh yeah, you could have said a comma a. Yeah, you could have replaced it all with the same new variable letter. Absolutely. There you go. DNE means does not exist. Mathematicians have abbreviations for everything. Okay, I'm going to stop there.